Why does fire exist? Simple question. You've seen fire 1,000 times. Campfires, candles, stoves. You strike a match, something burns, flames appear. But why? Most people never ask. Fire just is. It's hot. It's bright. It destroys things. That's all you need to know, right? Wrong. When you really ask what fire is, when you dig into what's actually happening when something burns, you discover something so beautiful, so perfectly connected to everything else in nature, that it changes how you see the world. Fire is a window into how atoms behave, how energy moves, how the sun powers everything, and why trees exist in the first place. And here's what's going to blow your mind. You're on fire right now. Not metaphorically, literally. Let me show you. Start with a piece of wood. Dead tree, sitting there, doing nothing. And air. Oxygen in the air, floating around, also doing nothing. The wood has been sitting there. The oxygen has been there the whole time. Nothing's happening. They're just there. But here's the thing. The atoms like each other to different degrees. Oxygen, for instance, would love to be next to carbon. And if they get close enough, they snap together. But there's a problem. If they're not close enough, they repel. They bounce off each other and go apart. So they don't know they could snap together. This is the fundamental tension. Carbon and oxygen want to be together. Being together releases energy. A lot of energy. That's the stable state, the low energy configuration. But to get there, they have to first get close. And getting close means climbing over a barrier. Let me show you what I mean. It's like a ball trying to climb a hill. And on the other side of that hill, there's a hole. A deep one, like a volcano crater. The ball is rolling along. It doesn't fall into the deep hole because every time it starts climbing the hill, it doesn't have enough momentum. It rolls back. But if you could make that ball go fast enough, it would crest the hill and fall into the hole. That's exactly what's happening with wood and oxygen. Oxygen molecules are constantly hitting the carbon in the wood. Millions of collisions every second. But they're not hot enough. They just bounce away. The atoms are bouncing off each other constantly. They hit, they bounce, they separate. Over and over. The wood just sits there. The oxygen just floats around. Nothing changes. This can go on for years, decades, centuries. A piece of wood can sit in the presence of oxygen for 1,000 years, and nothing happens. The atoms want to react, but they can't get over that barrier. It's frustrating when you think about it. Everything is ready. The carbon is there. The oxygen is there. They desperately want to combine. But without enough energy to get over that initial hump, they just wait. A few of them come fast. They go over the top, so to speak. They come close enough to the carbon, and they snap in. And that gives a lot of jiggly motion. That jiggly motion might hit some other atoms nearby, making those go faster so they can climb up and bump against other carbon atoms. And they jiggle, and they make others jiggle. And you get a terrible catastrophe, one after the other. All these atoms going faster and faster, snapping in. The whole thing is changing. That catastrophe? That's fire. It's just a way of looking at it. And once it gets started, it keeps on going. The heat makes other atoms capable of reacting, to make more heat, to make other atoms react, and so on. This is the key to understanding fire. It's not that something magical happens when you light a match. It's that you're giving a few atoms enough energy to get over that barrier. And once they do, they release energy. That energy makes other atoms move faster. Those atoms get over the barrier. They release more energy. It's exponential growth. One reaction triggers two. Two trigger four. Four trigger 8. The number of reacting atoms doubles, and doubles, and doubles. Within a fraction of a second, you have billions of atoms all snapping together simultaneously. That's why fire explodes into existence. It's not gradual, it's sudden. Because it's a chain reaction. A runaway feedback process. So this terrible snapping is producing a lot of jiggling. A lot of atomic motion all at once. And if you put, say, a cup of coffee over that mass of wood that's doing all this, it's going to get a lot of jiggling too. And that's what the heat of the fire is. So this terrible snapping is producing a lot of jiggling. A lot of atomic motion all at once. And if you put, say, a cup of coffee over that mass of wood that's doing all this snapping and jiggling, it's going to get a lot of jiggling too. And that's what the heat of the fire is. Heat is not a substance. It's not a fluid that flows from one place to another. Heat is atomic motion. The faster atoms jiggle, the hotter something is. The slower they jiggle, the colder it is. That's it. That's the whole story. When fire releases energy, that energy goes into making atoms move faster. That's heat. That's temperature. That's what you feel when you hold your hand near a flame. Think about that for a second. When you say something is hot, you're really saying the atoms are jiggling fast. When you say it's cold, you're saying they're jiggling slow. Fire is not a substance. It's not a thing. Fire is a process. It's this catastrophic chain reaction where atoms are snapping together faster and faster, releasing energy, making other atoms move faster, which makes more atoms snap together. It's a cascade, self-sustaining. Once it gets started, it feeds on itself. The heat from the reactions provides the energy needed to make more reactions happen. That's why fire spreads. That's why it's hard to stop. The heat makes atoms jiggle fast enough to react. The reactions produce more heat. More heat makes more atoms react. Around and around. A feedback loop. And the only way to stop it? Break the loop. Cool it down. Remove the fuel. Remove the oxygen. Cut one leg of the triangle and the whole process collapses. Well, it came from a tree. And the substance of a tree is carbon. Where did that come from? This is one of the most beautiful misunderstandings in all of nature. Everyone knows trees grow from the ground. You plant a seed in soil, water it for years, the tree grows big and heavy. Obviously, it came from the soil, right? Wrong. The carbon in the tree comes from the air. It's carbon dioxide from the air. People look at trees and they think the substance comes out of the ground, that plants grow out of the ground. But if you ask where the substance actually comes from, you find something extraordinary. Trees come out of the air. They surely come... No, they come out of the air. The carbon dioxide in the air goes into the tree and it changes it. The tree kicks out the oxygen and pushes the oxygen away from the carbon, leaving the carbon substance with water. Water comes out of the ground, you see. But how did it get in there? It came out of the air, didn't it? It came down from the sky. So in fact, most of a tree, almost all of the tree, is out of the air. There's a little bit from the ground, some minerals and so forth. The minerals give you the ash when you burn wood. That tiny bit of residue left behind? That came from the ground. But the wood itself? The bulk of the tree? The substance that burns? That's carbon from the air. That's water from the rain. Almost nothing came from the soil. Now, let me prove it to you. Take a pot of soil. Weigh it carefully. Plant a seed. Water it for years. Let the tree grow big and heavy. Now, dig up the tree and weigh the soil again. The soil weighs almost the same as it did before, maybe a tiny bit less. Some minerals got absorbed. But the tree weighs hundreds of pounds more than it did as a seed. That's roughly 90 kilograms or more. Where did all that mass come from? Not from the soil. The soil didn't lose hundreds of pounds. It came from the air. This experiment has been done. A Dutch scientist named Jan Baptist van Helmont did it in the 1600s. He was trying to figure out where plant mass comes from. He weighed everything carefully. The soil barely changed weight. The tree gained enormous weight. He concluded correctly that the tree did not come from the soil, but he thought it came from the water. He was close. The water is part of it, but most of the mass? It's carbon pulled directly out of carbon dioxide in the air. Now, of course, I told you the oxygen and carbon stick together very tight. How is it the tree is so smart as to manage to take the carbon dioxide, which is the carbon and oxygen nicely combined, and undo that? So easy. Life has some mysterious force? No. The sun is shining. And it's the sunlight that comes down and knocks the oxygen away from the carbon. The tree isn't smart. It doesn't have some mysterious life force. It's not doing anything clever. The sun is doing the work. Think about what that means. Sunlight travels 93 million miles. That's about 150 million kilometers from the sun. It takes about 8 minutes to get here. Those photons hit a leaf, and they do something extraordinary. They provide the energy to rip carbon dioxide apart. Carbon and oxygen are stuck together very tightly in CO2. Remember the volcano analogy? Carbon and oxygen want to be together. That's their stable state. To pull them apart, you need energy. A lot of energy. Where does that energy come from? The sun. The sun is pumping energy into the system. Real physical work. Photosynthesis isn't some magical process. It's energy-driven chemistry. The sunlight hits the chlorophyll in the leaf. The chlorophyll absorbs that energy. And that energy is used to break the bond between carbon and oxygen. The tree keeps the carbon, builds itself out of it. And the oxygen? The tree spits it back out. Oxygen is a waste product. Think about that. The oxygen you're breathing right now? Trees don't want it. They're getting rid of it. It's garbage to them. But to us, it's everything. So photosynthesis is really just this. Sunlight provides energy to. Tree rips CO2 apart to. Tree keeps carbon to. Tree dumps oxygen. It's the reverse of fire. Fire snaps carbon and oxygen together, releasing energy. Photosynthesis rips them apart, absorbing energy. Exact opposites. Mirror images. And that structure the tree builds? That carbon framework held together by chemical bonds? That's not just matter. That's stored energy. The tree spent years collecting sunlight, photon by photon, day after day, season after season. Every ray of light that hit those leaves, Every bit of energy absorbed by chlorophyll went into building that structure. A small sapling becomes a massive oak. 50 years, 100 years. Some trees spend 500 years collecting sunlight. All that energy stored patiently in chemical bonds. Carbon atoms linked together in long chains. Cellulose, lignin, the structure of wood. And then someone lights a match. All that energy, all that sunlight, released. Fire is just stored sunlight escaping. That's not a metaphor. That's literally what's happening. When you burn a log, you're watching the sun shine again. The light flickering in the flames, those photons, they're not new. They're recycled. Sunlight that fell on leaves 5 years ago, 10 years ago, 50 years ago. Stored as chemical bonds. Released all at once. Every photon from fire is a recycled photon from the sun. Energy in is sunlight. Energy out is firelight. The tree was a battery, a very slow battery, charging for decades. And fire? Fire is the battery discharging. Think about sitting by a campfire. That warmth on your face? That's not just heat. That's sunlight from years ago finally reaching your skin. Photons that fell on a forest somewhere, got absorbed by leaves, got converted to chemical energy, sat there waiting. And now they're completing their journey. From the sun to a leaf, to wood, to fire, to you. It's a chain. Sun to tree, to fire, to you. When you feel the warmth of a fire, you're feeling the warmth of the sun. Just delayed. Years delayed. Sometimes decades delayed. Isn't that extraordinary? The same energy, the exact same photons, just taking the scenic route. Sun to leaf, 8 minutes. Leaf to wood, years. Wood to fire, minutes. Fire to you, instant. And here's the beautiful part. This isn't special to fire. Every time you eat food, you're eating stored sunlight. Plants absorb sun. Animals eat plants. You eat plants or animals. The energy in your food? All solar. All stored. All waiting. Fossil fuels? Same thing. Coal is ancient trees. Oil is ancient plankton. Gas is ancient organisms. All solar energy. Just really old. 300 million years old. When you drive a car, you're burning sunlight that fell on Earth before dinosaurs existed. When you turn on a light powered by coal, you're releasing photons from the Carboniferous period. Sunlight doesn't disappear. It transforms, gets stored, gets passed around, and eventually gets released. Fire is just one way of releasing it. The fast way. The dramatic way. Now you might ask, why doesn't wood just spontaneously catch fire? If the energy is stored, why does it need a match? Remember our volcano analogy? The ball sitting on the hill. The deep hole on the other side. The ball wants to fall into the hole. That's the stable state, the low energy configuration. But it can't just teleport there. It has to climb over the hill first. That hill? That's called the activation energy. The energy you need to start a reaction. The minimum investment required before you get the payoff. Wood and oxygen are that ball. They're sitting there. They want to react. They want to snap together and release energy, but they can't. not without getting over that barrier first. The match provides that initial push. A match is just concentrated heat. Friction makes the match head hot. The heat makes a tiny area of atoms move fast, very fast, fast enough to get over the barrier. Those first few atoms react. They snap together. They release energy. That energy makes nearby atoms move faster. Those atoms react. Those release more energy. The match doesn't provide much energy, not compared to the fire that follows. But it provides it in the right place, at the right time, just enough to get the ball over the hill. Once that first reaction happens, the energy released is enough to trigger the next reaction, and the next, and the next. This is why fire is so hard to start, but so hard to stop. Starting it, you need to overcome that activation energy. You need to get atoms moving fast enough in one spot. Stopping it, you need to break the chain. Cool things down. Remove fuel. Remove oxygen. The same principle applies everywhere. Rusting is just slow fire, iron reacting with oxygen. But the activation energy is low. It happens at room temperature, just very, very slowly. Explosions are fast fire, very low activation energy, very fast chain reaction, over in milliseconds. Fire sits in the middle, fast enough to be dramatic, slow enough to be useful. And now you understand why. Remember what I said at the beginning? You're on fire right now. Not metaphorically, literally. Let me show you what I mean. You eat food, apples, bread, meat, vegetables. All of it is carbon-based molecules, complex structures built from carbon, hydrogen, oxygen. Your body breaks these down, not with flame, not with heat, but with the same fundamental reaction. Carbon meets oxygen. They snap together. Energy is released. Exactly the same equation as fire. Exactly the same chemistry. The only difference? Speed and control. Fire is fast and chaotic. Thousands of reactions happening at once. Temperature soars. Light blazes out. Your body is slow and controlled. The same reactions, but happening one at a time. Carefully. Precisely. Your cells have enzymes, molecular machines that manage the reaction. They make sure it happens at the right rate. Not too fast, not too slow. Just fast enough to power you. Think about what that means. Every breath you take brings in oxygen. That oxygen goes to your cells. Your cells use it to burn the food you ate. And you breathe out carbon dioxide. The same carbon dioxide that fire produces. Because it is the same reaction. You are on fire. Every cell in your body is slowly burning, combining carbon with oxygen, releasing energy. The warmth you feel? Your body temperature of 98.6 degrees Fahrenheit, that's 37 degrees Celsius. That's combustion heat, generated continuously, every second of every day. You're a controlled burn. Here's the beautiful part. Where did the energy in your food come from? Plants absorbed sunlight, built carbon structures, stored solar energy. You ate those plants, or you ate animals that ate plants. Either way, you're eating stored sunlight. And when you breathe, when you move, when you think, you're releasing that sunlight. Slowly, carefully, but releasing it. The energy powering your brain right now? Sunlight that fell on a field somewhere, got absorbed by wheat, got baked into bread, got eaten by you, and now it's powering your neurons. You are fire, just burning slowly enough to think about it. Every living thing on Earth is doing this. Every animal, every person, every creature that breathes. We're all slow fires, controlled burns, releasing stored sunlight to power our existence. That's not poetry. That's chemistry. That's physics. That's what fire really is. So now you understand fire. Not just what it looks like, not just how to start it, what it actually is. But let me show you one more thing. The chemistry of what you're seeing when you look at a flame. When carbon and oxygen snap together, energy gets released. That energy makes nearby atoms move faster. But some of that energy does something else. It kicks electrons to higher energy levels. And when those electrons fall back down, they emit photons. Light. That's what you're seeing when you look at a flame. Electrons jumping up and falling down. Billions of times per second. Each fall releasing a photon. Different atoms emit different colors. Meta, sex, 1.0. Copper burns green. Sodium burns yellow. Potassium burns purple. That's why fireworks work. You're not painting the sky with colored powder. You're choosing which atoms to burn. And those atoms emit specific colors based on their electron structure. Now, what about smoke and ash? Smoke is just unburned carbon particles. Tiny bits of wood that got hot enough to float away but didn't quite get enough oxygen to fully react. Ash? That's the minerals from the soil. The stuff the tree pulled up from the ground. It was never going to burn, it just gets left behind. Everything else, the carbon, the hydrogen, the oxygen, turned to invisible gas and drifted away. CO2, water vapor, gone. Here's something beautiful. In zero gravity, fire doesn't rise. There's no up for hot air to float toward. Fire becomes a perfect sphere, burning slowly, almost meditatively. A glowing blue orb hovering in space. No flickering, no dancing. Just a calm, steady burn. Different rules. Same chemistry, carbon and oxygen. Still wanting to be together. Still snapping in place. Still releasing stored sunlight. Even in the vacuum of space, the fundamental truth remains. Atoms like each other to different degrees, and when they find the right partner, they release energy. That's fire. Everywhere in the universe. So what is fire really? It's not just a thing that happens. It's not just hot gases and glowing particles. Fire is atoms finding each other. Carbon and oxygen, separated for years, decades, centuries, finally snapping together. Fire is stored sunlight escaping. Every flame you've ever seen is the sun shining again. Photons that traveled 93 million miles, 150 million kilometers, got absorbed by a leaf, got stored in chemical bonds, waited patiently, and now, finally, are completing their journey. Fire is the universe releasing tension. Carbon and oxygen want to be together. The tree held them apart using the sun's energy. When you light that match, you're releasing them. You're letting nature do what it wanted to do all along. And here's what should stay with you. You are fire. Not metaphorically, chemically, physically, right now. Every breath you take feeds the slow burn inside you. Every beat of your heart is powered by carbon meeting oxygen. Your body temperature, 98.6 degrees Fahrenheit, 37 degrees Celsius, is the heat of your personal combustion. You are sunlight, transformed. The energy in your muscles right now? Sunlight that fell on a field somewhere, got absorbed by plants, got eaten by you. And now it's powering your thoughts, your movement, your existence. So next time you see a flame, remember what you're really seeing. You're watching the sun shine again. And when you breathe, when you feel warm, when you move, remember you're doing the same thing, just slower, just more carefully. You are fire, carefully controlled. And that's not a metaphor. That's physics. If this changed how you see yourself, even a little bit, drop a comment below. Tell me what clicked for you. Subscribe if you want more physics explained the way Feynman would have explained it. No memorization, just understanding. And I'll see you in the next one.